I'm Dodi Cohen. I'm the VP of Product Marketing here in DriveNets, and DriveNets is the company that brought you the network cloud. And basically what we do is we enable service provider to make those cloud of theirs that we're going to dive into built like cloud and save the money, allow them to scale the network, and allow them to innovate much faster. Before we go into who is DriveNets and why do we do that, I want to just set things straight with regards to what is it we do. Because DriveNets does not do routers. Well, we do routers. We do excellent routers, but we do not do only routers. And I want to share with you the architecture of our solution so we will have alignment on what are we talking about when we talk about network cloud. So basically, DriveNets take commercial off-the-shelf hardware, namely white boxes that has resources like compute resources and networking resources and any type of processing units resources, and abstract those resources, abstract this hardware towards an application layer. So DriveNets brings the light blue parts of what we see. The white boxes come from another vendor. We are a pure player software company, and we do the network hypervisor, the abstraction layer. We have APIs towards applications. We also do very, very good routing applications. Whatever routing instance you want, we can run over this shared infrastructure, but we also support coexistence of third-party applications over our infrastructure. So if you want to have a router and next generation firewall and maybe some kind of DDoS mechanism on the same hardware, you can do it with DriveNets. And of course, towards the northbound, we have an orchestration that bundles it all together and connects to your OSS and BSS. So this is what we do. Why do we do it? And how did it all start? DriveNet started some 5 or 6 years ago with 2 industry veterans that just completed their exit of their previous startup. Ido Susan sold IntoSale to Cisco, and Hillel Kubrinsky sold Interwise to AT&T. And together they gathered up and thought, what problem should we solve now? What needs in the networking or technology world solving that we can bring and make a difference? And they decided to change the way networks are built. And I will talk about it in a minute. Why do we need to change the way networking infrastructure is built? It's been built practically the same way for around 20 years, and it works fine. But there is some issues there, and these issues are exactly what we try to resolve and hopefully succeeded. Since then, we have evolved in several paths. We have raised some money. We raised over $200 million earlier this year with a valuation of more than $1 billion. We have almost 400 people working for us. More than half of them are R&D. We succeeded in connecting and influencing some major bodies in the network like the Open Compute Project and the Telecom Infra Project. We launched an alliance together with VMware and Vapor.io called the Open Grid Alliance in order to change the way the internet is built. But most importantly, we progressed with technology and with customers. One customer we can name is AT&T. We are actually running live customer traffic in the AT&T IP/MPLS core network in North America. And we have multiple additional tier 1 providers, service providers that hopefully are watching us today all over the world that are either running our software as part of their networking infrastructure or in advanced stages of testing and proof of concepting our solution in their labs. So this is what we've been up to in the past 5 years. Why are we doing that? What is this problem that needs to be solved? The problem is the business case of service providers, of telco service providers, because we all know the capacity is going out the roof because of over-the-top services, because of the unicast nature of video services, because of Zoom that we are on now and the way we use it since the COVID pandemic started, because of new access technologies like 5G and fiber to the home and Wi-Fi 6 and 6E that resolved bottlenecks and pushed a lot of traffic into the network. So there's a capacity explosion, there's a service explosion, and operators need to pour a lot of money into the network. On the other end of the equation, this network does not bring additional revenues, or it does not bring the amount of additional revenues that is necessarily to maintain return on investment on the money they pour into the network. So something needs to change. The complexity of the way networks are built today, the inherent inefficiency of the way networks are built today in a monolithic architecture with one box per network function, cripples them. It does not allow them to make a business case for and remain competitive. And what they look at in Envy in order to learn from, and as a new type of competition, are the hyperscalers, those cloud providers, because those exact cloud providers that now, in some cases, steal some of their business with enterprise customers, et cetera, are exactly the ones that resolved a very similar problem around a decade ago in the IT world. Because a decade ago, you had the data center concept in which you have servers, you have applications running on servers, and it was a mess because you had a server per application. For a couple of applications, you need to purchase the hardware, you need to install, you need to maintain, you need to scale it up, et cetera, and then came AWS and GCP and Microsoft Azure and Oracle and IBM, the Chinese giants, and did it differently. They used commercial off-the-shelf hardware. They used merchant silicon that started building their own hardware, but they also created a shared infrastructure in which they run multiple functions in containers over the same blur of hardware infrastructure. And we'll look at that and say, hey, this led to cost saving, this led to incredible agility in terms of scaling, in terms of geo flexibility. And of course, the great thing about it, that it also enabled new services, the very fast launch of new services. You simply take the software, put it in a container. You don't care about what's underneath. You don't care about how many resources you have, and you have a new service. And what we say is, hey, let's just copy this concept into the networking world. And this is exactly what we do. We took the cloud concept and copied it into the networking world, and we allow operators to leverage this in order to reduce their cost, because we're a software company. We are doing commercial off-the-shelf hardware. So our business case is not based on hardware, so we can let you, as a service provider, use lower-cost hardware. We actually have the unique position to optimize the way the network is built, so you will need the minimum amount of hardware you need to use. So not only use lower cost hardware, you use less hardware in your network. And if you think about it, the other networking companies makes a lot of money out of their hardware business. So there is an inherent conflict of interest. If they want to optimize their software and use less hardware, they will cannibalize their business because of their lucrative hardware business. We are a software player. We can optimize what we do in order to make your network efficient in terms of cost. There are also savings in operational cost and planning and flexibility in terms of where you locate the network functions. Everything leads to lower cost. We also deal with the scaling issue. You need more capacity, you need more sites, you need more services, no problem. Our scaling is granular. You don't have to forklift and replace one big router with another much bigger router. You simply add white boxes, and I will talk about it in a minute. The third thing is handling the top line of your balance, because it handles revenues. We allow you ease of innovation. We allow you to fastly deploy new services and create new revenue stream, approach new target customers without having to send people to the site, without having to deploy new boxes at remote sites. So these are our benefits for service providers. How do we do it? What's different between what we do and your basic day-to-day disaggregation? Running VNF over a server, or taking a white box and running routing software on it. So we do disaggregation. This is the basic. We are a software company. We run over commercial off-the-shelf white boxes with merchant silicon, and then we take it couple of steps further. So not only do we do disaggregation, we also reduce the number of flavors you need in your hardware. That is, you do not need one small white box for your smaller size, a medium white box for your medium size, etc., etc. We are built upon just a couple of basic building blocks, just two main white box types.
Can you go back one slide? So you have on here minimize footprint at the edge. I want to tease that apart a little bit more because a lot of service providers are looking more at a smart edge, dumb core type of architecture.
There are two ways in which we minimize the footprint at the edge. One is that we are a much more efficient infrastructure in terms of networking functions than your day-to-day VNF. I'm going to touch it in the next slide, but let's talk about it now. When you do, for instance, VNF and run a network function, and I'm talking primarily about data plane network functions that need to run a lot of traffic through it. If you do it over a server, the CPU, the compute base of the server is not optimized for I/O tasks. So you need more and more servers, and you'll spiral out of control when your capacity ramp up. We do it over white box, which are optimized for networking with ASICs that do the I/O tasks in an optimal manner. So basically, if you compare function to function, we need lower rack space on the edge side. The second thing, and maybe the more interesting thing, is that when you talk about edge, you talk about edge cloud, etc. In nowadays, those sites are usually a mixture of compute instances and networking function. The network is an integral part of the cloud moving to the edge. And for service providers, when they do an edge function or an edge site, they need their server applications running on top of them, etc., and their networking. What we do is we combine both. So we have a single solution that abstracts the compute resources and the networking resources, meaning the CPU and the networking processor and the TCAM resources and the ports. Everything is blended together and abstracted towards the application, so any application can run on a compute resource or a networking resource or in a combination of both. This means you need less boxes at the edge side because you run multiple applications over the same box, and those boxes are optimized for networking functions, hence they are smaller. I hope this makes sense.
Yeah, so to distill that a little bit, basically you're saying that you're able to run more functions more efficiently in a smaller physical footprint, not necessarily a smaller service offering footprint. You're mostly addressing just the physicality of it and the ability to do more with less. Is that?
May I just piggyback? You're consolidating many applications, network functions, and some other things. Then how did you plan to address then the fate sharing that having a virtualized solution then entails? Because if we are consolidating everything, it means that if something fails, then everything is going to fail. How do we then plan to, well, address the situation? Let's suppose that there is a problem and then one of these massive servers is failing. Then what's going to happen with my services? Is there a way I can move things around? It sounds more of the case of a hypervisor type of deal in which we address resources and movement from one cluster to another. But do you have then a way to address this, or is this just abstracting resources and letting the application do it?
Absolutely so. Basically, I mentioned that our applications or our infrastructure is built like cloud. This is cloud native. And when we talk about cloud native, there is a separation between the hardware layer and the application layer. The hardware layer is a set of white boxes, and this set could be and usually is a high availability set, meaning there are white boxes backing up white boxes. And basically, the application layer does not reside on a specific hardware instance. So you have separation between the applications and the hardware. So if one white box fails altogether or lacks resources, you can seamlessly migrate this functionality to another white boxes within the cluster. But also there is an isolation between the service instances or network application themselves, because they run inside Docker containers. So if you have multiple network functions and applications that run on top of the same infrastructure, everything is isolated. So if you upgrade one, you do not touch the other. There is no common operating system or common software layer that can fail and hurt all the applications. Each application runs inside its Docker container and has a set of resources which is dynamic, meaning that if a resource, a white box that contains a port or a TCAM resource or networking or compute resource that serves this application, if it fails, then the hypervisor layer, the orchestration layer, immediately redirects this set of resources to the available white boxes and therefore maintains the application availability or survivability. The blast radius is very small for any type of incident in this type of architecture.
Okay, at the risk of being picky, so what happens with the layer when these with the virtualization layer? And I'm asking this because I've been in situations in which we have a massive white box with several services running on, and then suddenly what fails is not the service itself, things on the data plane. These are consequences, but the first thing, the cause of it is that the software that maintains the white box alive is what fails. So, and then how do we address that when the failure is not at this level at the top, but actually at the bottom?
The idea is to have high availability on all levels. Unlike a chassis-based solution in which you are limited in the number of redundancies you can have, here we can run a totally separated, highly available cluster that runs not only multiple white boxes that can take over in case of hardware failure, but also redundant or virtualization layer or hypervisor that can take over in case of this catastrophic failure you mentioned. So just going back to our previous notion, we did distribution. So, okay, we do disaggregation. We separate hardware from software. Now, what we do is eliminate the need for multiple flavors of white boxes. That means that we are built upon two types of white boxes that stack up, but still when they stack up into a cluster that can contain 3, 5, 10, tens of white boxes, we still have this hypervisor, this layer that wraps it all together into a one unified shared pool of resources. That means that from the application level, it looks like it runs on a single box. It does not care that it runs on multiple boxes, on a mixture of ports and TCAM resources and compute resources from different boxes. It looks like a single hardware instance for any application that runs above. So this is what we call distribution, turning multiple white boxes into a cluster. The next step is containerization. That means that it does not make sense to build such a fancy cluster with a lot of capacity and run only one application on top of it. So here comes the cloud native approach of running containers, Docker containers in which we can run DriveNets routing solution and third-party security or access or analytic solution, whatever you want to run on a networking optimized solution. And the nice thing about it is that each and one of those run inside a container, Docker container, and acts as if it has its own dedicated hardware. So even though this hardware that is allocated to it is a mixture of ports and TCAM resources, etc., from different white boxes, it sees it as a dedicated, unified set of resources, and it feels like it runs on a dedicated box. And of course, it is isolated from the rest of the application. So both from blast radius perspective and from manageability perspective, we're talking about different, totally separated network functions. So this is containerization. And after we did that, we did disaggregation and distribution and containerization, we got a mess. So we got something that is very, very hard to manage, etc. And there comes the orchestration. The DriveNets orchestrating system, or DNOR as we call it, is something that not only mitigates the inherent complexity of a cloud-native architecture like ours, but also takes it a step further and provides automation tools for the operators to eliminate the mundane tasks of your simple tasks of day-to-day networking and focus their labor on a more productive approach. So the orchestration layer basically does auto discovery and zero-touch provisioning and everything that you see as given in a chassis-based solution, but also does a lot of other things that makes the operator life simple. Now, having said that, everything here is very much like your day-to-day cloud, like your AWS infrastructure. What differs it from those solutions? And the answer is networking optimized, because networking functions today, in most cases, are PNFs, physical network functions, monolithic hardware and software and middleware from the same vendor. There was a notion that partially succeeded going into VNFs and CNFs. So
can I ask a question back one slide right before this? I'm trying to slide in there. Okay, so let's talk about the connectivity that's required between these. When you have these different containers down at the edge, or from a distribution perspective, right? If you think about a developing country, or think about an area where you're trying to get into, you're trying to provide multiple virtual network services across multiple regions. The connectivity between, like, let's say location A, where you have your core functionality and your orchestration, and then location B, C, and D that are in different parts of a country. The connectivity that's required between those two. Can you talk a little bit about how you can segment that and separate those physically? That even though everything is virtualized, right? You don't have to have it in the same data center. What you can have in two different data centers, and what type of connectivity requirements you would have for that. Is this something that is going to be inhibited by LEO satellites? Like, can I take a cluster of this and throw it into South Texas, where I live, throw it down into South Texas, but have the main network function happen in Dallas, but that orchestration is being handled up there, but the connectivity is something like terrestrial microwave, or like satellite internet access, or something that's not directly connected via copper or fiber.
The cluster, as we call it, is an instance that resides in a single physical site. We are not talking about distributing white boxes across the entire nation or state or whatever, and treating them like a shared pool of resources. We are talking about a single site. It could be a core site, it could be an access site or an edge site, in which we scale up the capacity and the resources required by adding white boxes into a cluster, and they're then using this cluster as a shared resources for multiple network functions, multiple applications.
Okay, yeah, what I'm talking about, like on this, and this is a great diagram for this, where that L1, L2 transport, actually, I'm not even looking at the L1, L2 transport, the image to the right of that, on that bottom picture where it's got the two aggregation areas. I'm talking about in between where it says co-medium. I'm talking right there, yeah. What happens if I want to segment that across? What if I want to put everything to the left of that down in one country, or in one area, or in one city, and have everything to the right of that being in major data center areas, like any of the like Chicago, Dallas, Philadelphia, whatever it is?
I'll divide my answer into two. One, you do the same as you did by as if you built your network with routers, because basically per site you have a shared infrastructure for the multiple network functions. On the other side, you have, let's say, another cluster. The connectivity between them is unaffected by how we implement the infrastructure on those sites. You still need your fiber or wireless or LEO, whatever connectivity you need. The one thing, and of course, the hardware we use is a state-of-the-art hardware. So if you want to use, for instance, ZR or ZR Plus, to connect dark fiber and multiple wavelength without the need for DWDM equipment at the sites, sure, we support it. But again, this is not part of a solution. This is a layer between the sites.
Let me clarify my question a little bit more, because I'm not talking about the data that's coming from the person who's using it. What I'm talking about is whatever the control data is that goes back and forth, where you're sending the configuration and the orchestration and the control data down to that. What are the bandwidth requirements for that, or what are the latency requirements for that? Like, what information do you have to make sure is high priority versus low priority to be able to orchestrate that across multiple geographically disparate areas?
This is negligible. The amount of capacity we need in order to manage this this infrastructure is by far lower than the amount of capacity we handle on data plane. Bear in mind that, of course, as in any network, by the way, you need to prioritize the management slice of the network compared to other slices in order to maintain manageability. But again, we pose no special or no new requirements from the DCC, from the control plane for network management. Okay, just let's dig a bit into the architecture and compare it to the monolithic chassis. So if you take a monolithic chassis, a router, or whatever, you have the chassis itself, which provides the backplane and the power and heat dissipation, et cetera, and you have some types of cards, usually line cards for packet forwarding, and the fabric cards and the control plane cards, et cetera. What we do is very similar, only you don't have a chassis, because chassis are great, don't get me wrong. Chassis are excellent, very efficient manner of hosting multiple types of cards and applications. But chassis are also limiting in terms of the number of slots you have, in the capacity you have per slot, in the heat you can dissipate, and so on and so forth. What we did is we took those functions and put them on white boxes. So we took one white box we call the NCP. That is a commercial off-the-shelf white box that runs our software and becomes an NCP, which is the Network Cloud Packet Forwarder, which is the equivalent of the packet line card. We took another white box, and these are the two main ones, and called it the NCF. This is the Network Cloud Fabric, which actually does the fabric connectivity between the NCPs. So in order to get from one NCP to another in a cluster, you need to go via the NCF. And then we took the NCH, Network Cloud Hypervisor, which is practically a virtual chassis, because it takes all the white boxes and treats them as if it was a chassis. It auto-discovers them, it zero-provisions them, it reflects them towards the application layer, and the control plane and the application plane, all the resources, and it shares the resources between them. So this is what we do. This is how we created the virtual chassis out of multiple white boxes. And when you go to the network, it can host any type of application. So you have the same infrastructure and you have the same building blocks, but still you have very different sites. Because in the core sites, you need more capacity, and maybe you need not as much control plane, but the thing is that you can scale each plane, the control plane and the user plane. And in the user plane, the packet forwarding and the fabric, each of those is a separate entity, so you can scale it in its own pace. And basically, you can have one set of white boxes that hosts multiple applications on the core site. And when you go down to the edge site, you will probably have a single white box that hosts all of the applications, both the control plane and the user plane, and some kind of access applications. And as you can see, we can host applications from DriveNets, as I mentioned earlier, and from third parties. And Ron will talk about exactly that, on how do you add applications to your infrastructure in order to have faster time to service, in order to have this service agility or service agile network. That means that you can very, very promptly add services to your network. So this, I showed you this at the beginning. I hope it makes more sense now. We start from white boxes, which we do not make. So we have the interest to make it optimal in use and for you to use as little white boxes as possible, not you personally, the service providers. We have the hypervisor layer. We have the application layer with applications that come from DriveNets and from third parties. And we have the orchestration layer, which handles both the infrastructure part of the game and the services layer. This is our architecture. What, in terms of DriveNets products, we have two main products, the DNOS DriveNets operating system and the DNOR, the DriveNets orchestrator. And within the DNOS, you have the infra part, which handled the hypervisor functionality and all the NCPs and NCF we talked about, and the NCC, which is the network cloud controller, and the NCM, which is the network cloud switch, the management switch. And we have the application layer DNOS, which are all the different flavors of routing applications. So we have a core, we have access, we have aggregation, we have peering, et cetera, et cetera.
When you say networking hypervisor, are you referring to a hypervisor cluster that's dedicated to running these network applications, or is this a term that DriveNets has come up with to kind of riff off what a hypervisor is? Is this VMware? Is it KVM? Is it something else? Like, what do you mean by networking hypervisor? Could you define that a bit?
Okay, the networking hypervisor is a DriveNets developed software layer that takes the hardware and basically it does hardware abstraction. It takes the different resources of hardware, be it compute resources, TCAM, ports, networking, packet forwarding, et cetera, and abstracts them towards the applications via an API. So basically, it allocates each service instance, each application, a set of different resources from the underlying hardware layer, and it does it dynamically. So it can do recovery if something fails. It can do reallocation or additional allocation if the application lacks resources, et cetera, So this is basically what we do. We did not use a commercial off-the-shelf hypervisor like VMware because we found that we need a networking optimized hardware as an underlying layer. And what we have in the market as a hypervisor only does CPUs and GPUs. They do not know how to abstract networking dedicated hardware. So this is why we came up with this solution, which to some extent mimics what VMware does, but in the networking world.
Okay, and could you maybe go into how that compares to something like SAI, the switch abstraction interface? Because it sounds like it's more like that than a hypervisor to me. So maybe how those play together. I know you guys do some stuff with the Open Compute project and stuff, so I'd like to hear a bit more about that.
Okay, so SAI is more of an SDK that allows you to connect to the hardware layer, to the ASIC. What we do is a more broader approach in which we take multiple SDKs, we connect to multiple hardware instances, and aggregate them towards an API, towards the application. So we eliminate the need of each application to talk to each type of hardware resources in order to grab and manage the resources it needs. We use SAIs in order to connect to the underlying layer, but we reflect them in a unified manner towards the application. Okay, Chris? Okay, I see you nodded. Thank you. Okay, this is it. Just as a recap, we build networks like cloud. That means that we have a cloud-native software. We are an open platform, so we use white boxes. We do only software, and I can't stress this enough because it's essential to understand why do we do and why do we have the interest of making this as optimized as possible for the sake of the service providers. And of course, we use the virtualization, and we talked about it just now, the hypervisor. We use those white boxes as shared resources for multiple applications. And multiple applications are key to service agility.
So this slide says cloud native software. And then in the last slide, you mentioned about the hypervisor. So why you need a hypervisor? Because a cloud native can run on the bare metal. So you can run containers. And hypervisor means you're using virtual machines so I'm trying to stitch at one hand, you're saying containers and then you're talking about the hypervisor. So they don't go together,
Okay, I see your point. The hypervisor might be a bit of a misleading term. We use it internally because we like to think about it as some kind of virtualization layer that takes the hardware resources and reflects them towards the upper layer API. Still, what happens above the hypervisor is cloud native. That means that applications are running in Docker containers. They are separated from each other. They are using the same resources. And because we use the distributed hardware, that means that we use more than one machine in order to create this pool of resources, to create the infrastructure for the applications. We need the hardware, we need the hypervisor to group them together. Now, we are not tied to a specific hardware. We can use multiple types of hardware, and we make it transparent to the application layer, so they do not need to be built or to be written for a specific hardware type. This is why we have the hypervisor, but still everything that happens above the hypervisor is cloud native, microservice architecture, containers, you name it.